How's it going, Nate?
I'm tired. I had to get up at 7. I actually got up at 6:20 today. And I don't know why. And then I set my alarm for 7, and then got up at like 7:50.
Yeah, I had an 8:30 class too. I had to wake up around 7. I didn't really wake up though until like 9. I don't know. It's been a long week. I'm tired. How's having 5 classes? Is that worse?
I don't know. It's not that much worse because it's like only the extra 4 classes. Like actually an extra 4 classes, 2 classes a week.
Yeah.
The 4 was enough, I think. But I need to take it for my humanities, so.
Yeah.
I had trouble with this homework.
Really? How so?
Well, first of all my numbers were never clean. And then when I tried to calculate the gravity force using the elastic equation, I got numbers with like the E-4 at the end.
How would you use the elastic equation? There's no spring.
But gravitational force is like a spring.
It's not a spring.
That's tough.
It's just like a spring.
Well, where's the equation then? Because those are the only 2 equations I could find that would actually help with the with calculating the stop.
Well, so I ask you to, right? So I ask you to calculate the kinetic energy at the bottom of the hill, right?
We knew how to do that.
And we know how to do that. And then question number 3 says, according to your LOL diagram, how would the kinetic energy at the bottom of the hill be related to the gravitational energy at the top of the hill?
It's the same.
They're the same.
That's what I said for that question too.
So that's how you find the gravitational energy.
That makes sense. Although, is the kinetic energy just using the kinetic energy equation?
Yep.
I did something right.
Sounds like you mostly did it right. You just got stuck at the end.
Yeah, and then that was like after doing all the equations for all the numbers, then it was after 45 minutes. So, and then I got the E-4 and got stuck, so I just gave up. That's all right.
Well, you can fix it. I definitely won't grade it before tomorrow. I'm pretty pooped.
Yeah.
I'm not feeling a Lauren grading session this afternoon.
I thought this class was at 11:40.
Well,
That's what the first one.
Does it say 11:40 in Veracross?
No, but I thought last time you pushed it to 11:40, so it would be easier for like Jamie and stuff. Maybe the other way around. I don't know.
No, it's the other way around.
Oh, all right. Maybe
if Jamie is in an Asian time zone, I don't know if he is.
I don't know. My English class did that. Never mind. They made it earlier instead of later.
Yeah, science classes are usually second lunch. Not that it matters now. Guys, you gotta don't overload the dining hall.
Right. I woke up 10 minutes ago. So.
Oh, okay. Well, Daniel's here. Thanks everybody for showing up on time. Even a good idea to show up a little bit early, so thanks for that. It helps. Yeah, we got Connor, Ava, we got Owen, Nate, Jamie, Sydney, Soren, not seeing Peter. Okay, so I think we are missing Pippa and Peter. Did I miss those people? Oh, there's Peter. Okay, just missing Pippa. I bet she shows up soon. First thing I'd like to talk about is it's starting to be time to think about signing up for classes for next year. I'll be putting in some recommendations for which class I think that you might consider taking. If you are a sophomore, then that's kind of a dicey situation. I don't know your academic record or what classes you've had before. So I'm just going to assume that you're going into chemistry because that's the class that generally follows this. But if you're not for some reason because of your situation, then just let me know that and I will let you know what I think. It's also very important that you understand that honors chemistry is harder than this class. Cynthia, would you say that's true? All right, Owen would say so as well. I looked at the people last year who were in this class and then went on to take honors chem, and on average, those people scored about 5% less in honors chemistry than they did in honors physics. Okay, so if the thought of getting a grade 5% lower is really scary to you, then you really want to probably rethink going into honors chem. Okay, so that's what I'm going to tell you about that. So if you're, getting a last term, and this is all based on T2. This term, I don't think we can really say a whole lot about the grades this term. I don't think they're going to be good predictors of success in chemistry. But the T2 grades are usually a pretty good indication of how well you're going to do in honors chem, minus about 5%. Okay, so if you are in particular, where this really starts to come into play is that say you have like an 85 in this class, which isn't terrible, but that really puts you on the borderline of a C in honors chem, and maybe something to think about. Now, the 5%, of course, is an average, so some people are fine, others don't do so well. And I will say that only like 3 students' grades went up, and those grades did not go up by a lot, like 0.1% or like 2%. So going up by a lot is really, really not a realistic expectation. All right, so the other thing I will say is that honors chemistry has a requirement of algebra 2. So we were talking about courses for next year, and I was saying that honors chemistry has a requirement of algebra 2 honors or higher. All right, so if you are recommended for Algebra 2 next year, that is a good sign that regular chemistry is probably a better choice for you. All right, in fact, you don't actually qualify for honors chem, so you'll, that's a line there. And then I was also saying that grades almost always, 90% of the time, go down going from honors physics to honors chem. Go down by a significant amount, about 5% on average. So you might want to keep that in mind when signing up for classes next year. I'm not trying, I think it's a good course. I'm trying to scare you away or anything. I'm just saying that if you think this class was hard, you really haven't seen anything yet. Any questions about that? No, okay. So also in general, people in honors physics would often go into honors chemistry. That's the typical path. All right, let's talk about the homework. Okay. Okay. So were there any, it's difficult to see you all at once here, so please use the raise hand button if you need to get my attention. Although I can see you all. Any questions about the first few parts? Uh-oh. I love it when somebody just vanishes. I know that somebody vanished, but I don't know who it was. Yes, Pippa. You're still muted.
Sorry. So the ball diagram, was it just point A to just point A and point B, or point A to point B?
I'm not quite sure I understand the distinction.
Should there have only been 2 L's or 3?
2.
Okay.
So one L up here at the top of the thing, and the other L down at the bottom. Okay, and then what do you find? According to your LOL diagram, how would the kinetic energy at the bottom of the hill be related to the gravitational energy at the top?
They're the same.
Yeah, okay. Ben, did you have a question?
Oh, I was just going to answer the question.
Okay, so they're the same. So if you were to write that mathematically, it would look like this. All right, you'd say the gravitational energy at point A equals the kinetic energy at point B. So that's a very clean, simple way of expressing that idea. It's fine to do either way. There's advantages to using math. Okay. Did we have any problems with number 5? We all found the energy notes from April 13th and found the kinetic energy equation, right? Okay. And then for number 7, so what I'd like to do is I'm going to make you into breakout rooms, and I'd like you to do 7, 8, 9, and 10 just all at once. They're all really, of course, very closely related to each other. And then we'll come back together as a group and discuss that. I'll pick somebody to present. All right, so I will make some breakout rooms for you. And then you want to do 7, 8, 9, and 10. Okay.
Can everyone see that?
Yeah.
So I looked it up online and found that
No, can't do that. Not allowed.
oh, then maybe someone else should screen share. I think I did it wrong because I think I should have just taken the kinetic energy from above.
Yep.
All right. So someone else can share.
Because the number 3 says the kinetic energy at the bottom is equal to the gravitational energy at the top.
Yeah, I just realized that when you fixed it.
Yeah. Did somebody else do the,
Do you want me to share? I'll do mine. That's what I
Okay.
got for my graph.
does that look like a straight line?
Yeah.
I'd say so, right? All right. So what's your equation?
So I found the slope using 2 points. I think it was like the one at 0.3 and the one at 0.6. So then found that slope, and then I knew that the y value for the like y equals mx plus b, the y is the gravitational energy, the m is the slope that I got, and then the x is the launch height.
Can you show me your kinetic energy calculation?
This up here.
Hmm. How did you find the slope?
I used 2 points.
Oh, okay. Did anybody
Yeah.
get an average slope, like using a computer program?
What did you guys get for your slope? I just found mine.
I got 0.37. Same.
Yeah, that's exactly what I got.
Everybody just used 2 points?
Yeah.
Did you use the same 2 points?
I used the top and bottom.
Me too.
Hmm. Well, I think everybody probably got that, but I'm going to go check. I didn't actually check the website. I just hoped that it would give you the right answer. It's not right now, which is great. So I'm going to go check out a couple other rooms, see what they got. So what did people get for the for their answer?
Do you want me to share my screen?
Sure.
All right. I got this graph, which is pretty much a straight line. It's supposed to be going through the
Yeah.
0, 0, but it's, putting on the graph a little bit of error. So, and then is your graph line a straight line? If so, I said yes, and then I calculated the slope, which is 0.37 joules over meter, and then I got energy kinetic equals 0.37 joules per meter times the drop height.
Mm-hmm.
And then for 9, I got 0 because the drop height is 0, so it's gravitational energy.
Okay.
Yeah. And then, yeah, that's it.
So what's gravitational energy per meter?
For what? The
slope?
Yeah, so I don't really. So what my thinking was that when you plug it in here, right, the units for this are joules and meters, right? So wouldn't that mean it's joules over meters?
Yeah, no, that's right. It's joules over meters for sure. What is a joule over a meter? Is it anything else?
So isn't it? It's a unit of energy, right?
Mm-hmm.
Is
So it's a unit of energy over a meter. So it's however many joules is exerted of gravitational energy when the drop height is higher or lower. So, when you have a higher drop height, there's going to be a higher joules of gravitational energy.
Okay. So I sort of assumed, can you scroll up to your data table or do you order to the side? That's fine too. So you get 1.21 meters a second at the bottom.
Yeah. It's at least what I got. I think, shouldn't everybody get the same?
They did, yeah.
Okay.
Huh. All right. Well, we're gonna head back to the main room now.
Okay.
Everybody got the same answer in the other room that I saw.
All right.
Okay, so if we look at this activity here, I thought that they were doing it without friction. So if I come up to say 40 centimeters and I release the car, you got 2.42 meters a second. And that is some friction has been slowing down the car on its way down the track. If there's no friction, then it should be 2.8 meters a second. So it's lost some velocity because of friction. All right, so if we come back and look at our LOL diagram, right, our LOL diagram should have, oh, there's Alexander's. Our LOL diagram should have some friction in it. How do we put friction into our LOL diagram?
You just put some into the reservoir.
Yeah. So our LOL diagram is going to have some boxes leaving and going into the reservoir. So does that mean that our kinetic energy at the bottom is equal to the gravitational energy at the top anymore?
Nope.
No. So our gravitational energy at the top plus the amount going to the thermal reservoir, I don't know. I'm going to call that ETH. Okay. Is equal to, well, actually subtract, right? Subtract the amount going to the thermal reservoir is equal to the kinetic energy at the bottom. Okay, so this would be the gravitational energy. It would have some boxes. And then the kinetic energy over here would have some boxes. So the total amount of boxes stays the same, but you're going to lose some energy to the thermal reservoir. Okay. So that means that ultimately our slope is not going to work out the way that I had hoped. I should have checked that better. It works a lot better in person, I'll tell you that. So what did you folks find for the slope? Did anybody find some units other than joules per meter? Okay. How many of you got joules per meter as the slope? Okay, so that's good. All right, but remember, a joule can be simplified, or not simplified, but a joule is equal to something else. What's a joule equal to? Yeah, Ava?
I think it's a Newton.
A Newton times a meter. Right. So this joules over meters is equal to a Newton times a meter divided by a meter. What's that?
A Newton.
Yes.
A Newton. Okay. So what physical thing do you think that the slope represents?
Isn't it like the force the car has when it gets to the bottom?
Well, why when it gets to the bottom?
Because it's I guess it's because when we drop it, we are letting it get affected by gravity.
Okay. So what do you think it might be?
I thought it was the force of the car hitting the box.
Well, the car hasn't even hit the box in our experiment. Right, we're doing before when we drop it, and then right when it goes through the little magical speed detector, it hits the box after that. So how would it know the future? All right, Newton's kind of suggests a force. What force do you think it might be?
Force gravity.
Okay, force gravity. Force gravity on our box would be 0.5 newtons, right? And we got 0.37, but apparently the simulation has friction. So that actually slows it down and lowered the slope a little bit. Without friction, then this turns out to be the force of gravity on the box. So according to our equation then, the gravitational energy should equal the force of gravity on the object times how high it is. Right, the drop height. So that's the difference between where the object is now and whatever it is that you are using for your reference point.
Doesn't the mass affect it?
Well, so how do you find the force of gravity?
Oh, okay.
What do you mean, okay?
I mean, yeah, force of gravity is 9.81 times the mass, so I guess
Right.
that
So force of gravity, and you're welcome to round that to 10 if you want. Force of gravity is 10 newtons per kilogram times the mass. So therefore, the energy of gravity is equal to 10 newtons per kilogram times the mass times the height. Right, I can plug this in over there. So I'm going to add all this to our notes.
Mr. Schmidt, does this mean we're gonna have to redo the whole worksheet, including friction?
No.
Hmm.
Just say, oh, well, it should be equal to the force of gravity, but friction made it less.
But like the graph and all that stuff, just leave it the same.
Yeah, it's still a straight line.
Okay.
So the only thing that it affected is that it made the slope smaller than it should have been. So now we have an equation for gravitational energy. So force of gravity times mass, or sorry, times h, or 10 newtons per kilogram times mass times h. All right, and that's going to give you, if your mass is in kilograms, the kilograms will cancel, and then you'll have newtons times meters. So that'll give you newtons times meters. Okay, this is when you're near the Earth. Elsewhere, then you should use gravitational energy is equal to the mass of the object times the strength of the gravitational field, G times H. And that's really annoying. Why did they do that? You shouldn't break across this equation like that. That's bad programming. Okay, so now we have an equation for gravitational energy. Which, you know, went okay. But if I ever have to do this again, I'll have to find a different simulation. I hope I never have to do this again. All right, so we're now ready to start Energy Worksheet 3. All right, so I should copy it over to your homework folder, and then we'll go ahead and start with number 1 and try it in your small groups for a little bit. Then we'll come back together and see how that's going. Okay, we're not actually going to use this equation just yet, but definitely we will. So you want to keep it in mind and maybe copy all of these equations into like a useful equation slot. All right. Energy Worksheet 3 doesn't actually use it.
This is our homework as well.
It is. But I find that people don't often understand everything about it. So I'd like to go over the first couple of problems. Okay. right.
It really looks so hard. So annoying. The LOL diagrams just turn into really sad graphs.
These sad graphs.
Yeah, because they used to
Make
be LOL, just random, and now they have lines and
Oh,
you know.
So for the circle, we have gravitational energy, elastic energy, and then we have the two cars, I think.
2 cars?
Well, no, sorry. Yeah, just the one car.
Okay.
My bad.
Oh, is it one car in different situations?
Yeah, it's 1 car at
Yeah.
2 different moments in time.
So did you feel the spring in the car?
And elastic.
Do we have to include the spring in our system?
You don't have to,
That's
but
right, the track.
it helps.
Not the spring, the track.
No.
Okay.
So the track is really part of the thermal reservoir. So what clue do you have that there's not going to be a thermal reservoir here in this problem?
That it says there's no friction, but
Yeah.
the question literally says, assume the system consists of the car, the earth, and the track and the spring.
Well,
So I was just wondering.
yeah, the track's not going to do anything.
Okay.
Some people like to put their thermal reservoir inside the system. I kind of like what we've been doing and putting it off to the side
Yeah,
right
that's
next to it.
confusing. Because you would assume you can get it back if you just leave it in there.
Yeah, no, I agree. The people who wrote this worksheet like to put it in the system.
Can we assume that at position A the spring is loaded?
I think so.
Yeah.
Otherwise, how did it get launched?
It loaded after. I don't know.
That sounds a little convoluted. Let's assume that it's loaded now.
Dr. Schmidt,
Yeah.
what's ETH? Is it something we went over? I just forgot.
So what do you think it is?
Oh, is it that? Oh, I forgot the name. Yeah, I probably just don't know. Yeah. Is it thermal something?
So yeah, thermal reservoir.
Yeah,
That's what it is.
but
So,
there's no thermal reservoir though.
not in 1A, no.
Yeah.
You notice they use the same diagram for every problem. So those people who like to include the thermal reservoir in the system would put it there.
Okay.
What does qualitative energy conservation mean? Just what we did saying.
Yeah, that's one of the reasons I like to go over this problem before releasing you at it on homework. What do you think it means?
Just like what we did with the kinetic and gravitational energy, basically say like energy elastic equal at point A equals energy kinetic and gravity at point B.
Yep, that's what it is. All right, I'm gonna check out the other room, but we'll see how other people are doing.
Thank you.
It seems like you got a good start here.
Hi, Dr. Schmidt.
Hello.
I have
How
a
we doing?
good, except for like the qualitative energy equation.
Yeah.
I feel like we're missing something. No. All right. So can you show me what you've done so far?
I can share my screen.
Sure. Okay. So you're saying the elastic energy. Now, I would specify the elastic energy at point A. Okay. It's no confusion now because, okay, I guess you could do that. I like subscripts myself.
Okay.
I mean, I'm not going to mark it wrong or anything. I'm just, I guess I shouldn't make you do everything the way I do it. Okay, so that's what it is.
Is it?
That's it. It's just the equation that you write that describes how the things are equal.
Right. But now we're doing it without the spring.
No. Now we're saying there's a friction. So before there was no friction. Now there is friction. So what's the difference?
Wait, what?
For 1B.
The problem 1A for a frictionless system that includes the cart, the earth, and the track, but not the spring.
But are you reading the same thing I'm reading? It says and the spring.
For me, it says but not.
Oh, not the spring. Oh, okay. So do that.
Right. Would we just get rid of the elastic energy?
Yeah, there's no elastic energy then.
But then where would the energy come from?
Outside the system. Sorry, I think it's C that has friction. Yeah, it is. I don't think I ever woke up, Nate.
I'll be able to stuff for 30 classes. You can only wake up if you have like a 2 class.
Yeah. All right. I'm gonna go check out another room, but see what you can do with this equation.
Right.
Okay, so there's no spring. There's no elastic energy, there's no gravitational energy, and there's no kinetic energy at point A. There's nothing here. So how does it go?
What?
Well, so can I see your screen?
Yeah. So it says repeat the problem 1A for frictionless system that includes the cart, the earth, and the track, but not the spring.
Okay. So your first L looks fine. There's no elastic energy in the system because there's no spring, right? What would
There's
position
no-
B look like?
I mean, theoretically, it should be the same as above. It should just be 2 blocks of energy kinetic and 2 blocks of energy gravity.
Okay.
But where does that come from?
Well, can you finish doing your O?
Oh yeah, sorry. No, there's no spring, so it would be the cart. I guess the track, right?
Okay.
I guess the
and
track is on.
the
I
track's
don't
not
think
really
it exerts
important.
any. Yeah, so it'd just be the G cart.
Okay. So does that mean that there is no spring?
Yes. Oh no, the spring is just out of the system.
Oh, okay. Can you put it there outside of the system?
Yes.
Okay. So that's where the energy is coming from. Outside of the system.
How would we write the equation for that?
I don't know. Take a stab at it.
Is that it, or is there more? I feel like that's not really an equation.
Well, it is an equation, but it's only accidentally true. You just arbitrarily made the kinetic energy at B equal to the gravitational energy at B. Like you just chose two boxes for each.
Yeah.
Right. You don't have to. You could have 1 and 3, or any difference really.
But up here, it's like, the energy elastic is equal to the energy kinetic plus the energy gravity. But because
Okay.
because the thing that's putting the energy into the system is outside of the system.
So we can't write that into our equation?
I mean, I guess we could. Would just
Okay.
equation.
Well, it doesn't make sense to call it elastic energy because as far as the system knows, it's not elastic energy. It could be any energy.
So is it just like ETH or whatever it is?
Well, that would be thermal energy.
Oh, yeah, that's true.
Right. So it's just energy that's coming from outside. What would be a good way to write that?
Like EX or something? Just arbitrary.
Sure. So just arbitrarily calling it EX is fine. I'm going to suggest that we call it change in energy. So that we call it change in energy. Okay, because that gives us some flexibility. Maybe some energy is leaving the system.
Yep.
So the change in energy of the system is equal to EK plus EG.
Okay, but assume there's friction. That means there is thermal energy, right?
Yep. All right, I'm going to check out some other rooms.
Cool.
I think you got this. Just take a guess at it and see what happens.
Okay, thank you.
Okay. Somebody want to show me what you came up with?
For which question?
Number 1.
All right. I'll do it if no one else wants to.
Okay. A couple of comments. I would really recommend putting a subscript A there and B here and here.
Wait. What does that do?
Well, that tells you that we're talking about the elastic energy at point A.
Oh, okay, I gotcha.
Okay, so it could be that there's
Because it's different points in time. Yeah.
yeah. Like what if we somehow move this spring up here to B? I don't know. I mean, you could have a situation in which you have multiple kinetic energies or multiple gravitational energies. It's much less common to have multiple elastic energies, but it's still possible.
Mhm.
All right. So that just, I think it's just a good habit to get into.
All right, that
Okay.
makes sense.
All right. How about 1B? Okay, but here our spring is not in the system anymore. So I don't know that it's elastic energy. Right?
Yeah.
So what do you think I could call just any old system, any old energy coming into the system?
Applied.
Okay. Applied, I'm going to suggest, how about En?
All right. All right. Oh.
So just the energy coming into the system.
Okay. So would I keep this on for position A? Would it be?
No, the elastic, there's no spring in the system. So there's
All
no
right.
elastic energy in the system.
Would this work?
Yep, I think that's good.
All right.
All right. So it's not just En at A, it's just En, right?
Oh.
Because there's no A or B for change.
Uh-huh.
Okay. All right, seems good. I'm going to come back to the whole room there. I think your equations look pretty good, so if you wouldn't mind sharing them.
All right.
Okay, Connor has been voluntold to show us his equations. So you want to walk through those, Connor? We'll see if anybody has any questions. You're muted.
Yeah. So at the first point, there's obviously in 1A, it's all energy elastic. And then at point B, there's kinetic energy and gravitational energy.
Okay. Everybody understand what's meant by qualitative energy conservation equation? Okay. You really have to hit the raise hand button right now because it's the way Zoom works, it only shows you 4 at a time right now.
Do we have to do like the B and the A there? Okay.
What do you think, Connor?
Yeah, I'd say it's pretty important. Because you could have multiple, like say you're on a roller coaster, there's multiple like points with like energy gravity and energy kinetic where they're different. So you're gonna want to label them with what points they are.
Okay.
In 1B, I just called it energy in. And there was no exact point with that. There's no like A point or whatever. And then at point B, energy kinetic and energy gravity are equal to energy in. Good.
I'm not seeing any hands.
All right.
Can we just call it energy IN? Like, is there a specific name?
It's the energy coming from outside the system into the system. It doesn't have any particular name right now.
Okay.
Energy? Isn't like theta energy?
Theta energy?
Isn't that what you told me it was? The triangle?
Oh, so in your group, I called it delta energy.
Delta, rather, not theta.
So the change in energy.
Yeah.
That's fine too. I think I like energy in. It's pretty clear. It also raises the question of maybe there's such a thing as energy out.
All right. Should I keep going?
Yeah.
All right. And then in 1C, there's energy elastic. And I did 5 bars just because I don't know. And then so there's energy kinetic in position B, energy gravity, and energy thermal that leaves the system because it's not frictionless anymore.
So that's a kind of energy out. So you could also just call it energy out if you wanted to.
And then my energy conservation equation is energy elastic at point A is equal to energy kinetic at point B, plus energy gravity at point B, plus energy thermal at point B.
Okay. Oh, you already did D. You don't have to do D. Let's let other people do D. All right.
Okay.
So your homework then is to finish up this worksheet to the best of your ability, and I'll look forward to seeing what you do. And I'll be grading your gravitational write-up lab. I think that should be pretty straightforward, a good opportunity to get points. You just might want to fix up the last question based on our discussion today about what it means. Okay, so I definitely won't get to that till tomorrow. All right, I will hang out here if anybody wants to talk to me about anything, maybe classes for next year or whatever. And have a great Thursday.
Bye. Thank you.
Thank you.
Thank you.
Thank you. Actually, Dr. Smith, I just have one question about my
Yeah.
class for next year.
Sure.
Do you think that honors bio would be a good option? 'Cause I took honors chem last year.
Yeah, no, I think that's a natural progression for you, for sure. I think
Okay.
you
I'll
have to
speak with
take
my advisor
bio.
again, but she said,
Yeah, honors bio is fine. I have no doubt you will be successful in that class.
thank you.